Hello everyone, welcome to video 24 of chapter 3. In this video, we go through another example of linear programming. We call it LP5. It's an example taken from the textbook 3.6.2. In this example, we will show you that you could encounter systems where the constraint you don't need to add artificial variables for all the equations, but only as needed. Okay, so let's take a look. So here is our problem. Minimizing z restricted variable, and I have this constraint. So first of all, the constraints are not in standard form. I have less than sign and bigger than equal sign. Okay, so we need to first add slack variables to put it in standard form. So there are two inequality sign, therefore we will introduce two slack variables, x4, x5, one for each of them. So this we have done a long time ago, we should all know how to do. So for less than equal sign, you will add plus slack variable and change into equal. And the bigger than equal sign, you will add minus the slack variable and put it into equal. And the last equation I copy. Okay, and then we're still minimizing the same z under this is just a constraint. So now we see that we have a problem in standard form, but it's not in canonical form, so we'll take a close look at it. We see that earlier we talked about the advantage of adding slack variable is that it can make the equation into a canonical form. They can serve as a basic variable. So here we observe that, in fact, x4 can be used to serve as a basic variable because it's 0 in all the other equations. However, for x5, the situation is not so fortunate because it has a wrong sign. It's minus. So you could multiply this equation with -1 and make this plus x5, and then on the left-hand side, this could be a basic variable for a canonical form, but that is not so good to do in this example because if you do that, then you get a -4 on the right-hand side. And we say that we want to keep all the bi's on the right-hand side non-negative. So I can't do it. So this x5 is no good. So I will need to add two more artificial variables for the last two equations to introduce two more basic variables. Okay, so let's call this x6 and x7. They'll be added to the second and the third constraint. And then I define this w to be x6 plus x7. Okay, so hope that is clear, and let's go on. Okay, so once I have done that, and I find myself having a system in canonical form. So the first equation unchanged. For the second one, I add in x6. For the third one, I add x7. So now the constraint is in canonical form with the basic variables x4, x6, x7, and the right-hand side is non-negative. Okay, and then this line is the objective function z, and then you know we need to add the equation for w. So w is defined as x6 plus x7. So how do you obtain this equation, which the w is expressed in terms of the non-basic variables? Well, so keep in your mind that w is x6 plus x7. Therefore, you would take only this equation and that equation and add up the columns of the coefficients, okay? Not the first one. So let's look at x1 minus 1 plus 1 is 0, therefore I have nothing. And for x2, 0 minus 1 is minus 1, therefore I have plus x2. And for x3, I get 2, which is 4, so -4, okay? And then next is the x5. It gave me -1, so I put plus x5. And I do not do x6 and x7. They add up together, equal w, which go to the right-hand side, okay? And then the right-hand side here is 4 plus 4, which is 8, and it's -8. Okay, so you should know how you obtain this equation, okay? Even though in reality we could use LP Assistant to help us, and this equation could be set up automatically by the LP Assistant, and you still need to know where these coefficient comes from and how to calculate it and spot mistakes if you are doing this by hand. Okay, so the rest can be carried out in LP Assistant. I have made a separate video to show you how to set this up in LP Assistant, and how to set up artificial variables only for some of the constraints, not for all. So make sure to take a look at that. Okay, so there's some surprise in store in this example for us here beyond that. So if you have seen that video, then you would know how to set this tableau up. And after you set up, this is the tableau you would have, and it's the last canonical form. Also, we could actually type that in because we computed by hand as well. So we have this tableau. So your first goal is to stage 1 to minimize the W here. So we get a -4, and then we check the ratio here. This ratio is 1, that's 2, and that's 2. So I pivot here, and you will click here in the LP Assistant. Once you click here, and it calculates and it generates the second portion of the tableau. And then I see that I still have a negative sign. Then let's look at this column, and I have two candidates. This one has ratio 2, this one has ratio less than 1. Then I will pivot here and I click on that, and then you will get the third part of the tableau. And then I see that for the W, for this part, this optimization problem, I get all positive coefficients. That means the minimum of the W has been achieved. And then let's check the minimum value. It should be the negative of this one. So, wow, surprise, we have something that's not 0. So we now can conclude that the minimum of this W is negative of this, so it's 4/3, and it's strictly bigger than 0. And this is attained at the corresponding basic solution, which is x3 is 5/3, x6 4/3, x1 is 2/3, which is listed here. So what does it mean, the minimum of W is strictly bigger than 0? Well, we talked about it, right? Only when this minimum equals 0, then the original problem has feasible solutions. If this is strictly bigger than 0, then the original problem has no feasible solutions. Then you can terminate here. You don't need to go to stage 2. Then you stop, and the problem has no solution. Okay. So I hope that was clear and useful, and you enjoyed it. I'll see you next time.